Have you ever wondered what makes plastics plastic? Why different types of plastic have unique properties? And about how polymers can be used for medicine? Let's take a look at these questions in the context of carbonyl substitution reactions. Before we start talking about the chemistry behind how some plastics are made, let's take a step back and think about what the word plastic even means, and how plastics relate to the term polymer. A polymer is a large molecule composed of many repeated subunits, but that's a very broad definition. There are many key distinctions that can be drawn between different types of polymers, and one consideration is how polymers behave when heated. Some polymers can be melted down, molded into a shape, and then remelted and molded into a new shape. Plastic means able to be molded, and that's why these polymers are called thermoplastics, changed and molded again and again just by heating, which overcomes the intermolecular forces holding the plastic shape. When we call something plastic, we're talking about thermoplastics. Other polymers, called thermosets, are different. Once they're set into their shape and structure, that can't be changed. Examples are rubbers and epoxies. The thermosetting process creates an irreversible transformation, creating new covalent bonds that cannot be altered without breaking them. Today, the polymers we're going to be talking about are thermoplastics.
To help visualize how polymers can be synthesized, let's suppose we have two types of molecules as our starting materials, represented by these red and blue shapes. These molecules can react with one another to form a new bond. Imagine they're clicking together to form a chain of two monomers, a dimer. Early on, the most likely thing to happen next is for the red and blue monomers to click together to make more and more dimers. These dimers are capable of clicking with each other or with free monomers to continue growing the chain. As the reaction continues and the monomers are consumed, the growing chains will click together to continue making longer and longer chains. Because this method of polymerization occurs in a series of stepwise reactions that elongate the chains, this is called stepwise polymerization.
But how can these molecules click together, really? One reaction that you're probably already familiar with is used to create certain types of plastic through step growth polymerization. Nucleophilic substitution at the carbonyl by way of a tetrahedral intermediate. Attack by the nucleophile leads to a tetrahedral intermediate, which collapses to form a new carbonyl derivative. The leaving group X leaves with the nucleophile substituting it. Now let's apply what we understand from that mechanism to this specific situation and make a real polymer. On the left, we have a molecule with an amine group on each end, and on the right we have a molecule with an acid chloride group on each end. We've got a molecule with two nucleophilic ends and a molecule with two electrophilic ends. Think of these as the red and blue shapes that we talked about before. Now, what we know about nucleophilic substitution reactions tells us that the reaction will follow the mechanism we outlined previously and click together to give us a product like what we see below. But there's still an unreacted amine end and an unreacted chloride end on the molecule. Each end can continue reacting together, clicking together to produce a long chain of a polymer that may be familiar. Nylon 6,6. Nylon is used in a variety of familiar products in everything from toothbrushes to stockings to carpets. The properties of thermoplastics are heavily influenced by the intermolecular forces between multiple polymer molecules. In the case of nylon, the carbonyl oxygen of one strand can form a hydrogen bond with the proton on the amide of another. But this depends on how well the strands align with one another, and it's the alignment of the strands that ultimately determines the properties of nylon. Nylon is a thermoplastic, so it can be melted down, cooled, and take on its new shape without degrading. When nylon fibers are manufactured industrially, the polymer strands are melted down and spun, which begins to align the strands. The strands are further aligned as the fibers are drawn or stretched out to as long as 4 times their original spun length.
Kevlar, the polymer found in bulletproof vests, follows the same mechanism, resulting in the amide bond linkage between the two benzene rings. These benzene rings will have an important impact on the properties of Kevlar. We would expect to see hydrogen bonding between the amide groups of Kevlar like we saw in nylon. But unlike nylon, Kevlar has rigid benzene linkers between the amide bonds, instead of flexible linkers. This allows the strands to adopt a highly ordered microcrystalline structure, explaining its unique rigidity and strength. However, this actually presents problems for the manufacturing of Kevlar. Conventional methods, like heat or solvents, don't work to dissolve the fibers. Industrially, calcium chloride is used to disrupt the hydrogen bonding network to make Kevlar easier to process, but that must be removed in later steps. We would expect to see
Polymer chemistry has shaped our modern world, but there are many areas of active research and development. One area is the use of polymers for medical application. Imagine sutures or stitches made of polymers that can easily and harmlessly break down in the body. Now imagine that those monomers it breaks down into aren't just harmless, but useful drugs. You could use this to provide painkillers directly at the site of injury. That might sound far-fetched, but it's not. For example, polyaspirin is one such implementation being developed by former Rutgers professor Catherine Urich. The carbonyl groups on aspirin may very well be good sites for clicking together long strands just like what we've seen so far. The field of polymer chemistry will only advance with new innovations based on the same fundamental concepts we've been explaining.
And that ends today's lesson.
Thank you for watching.
And we'll see you next time on 100% Organic.